Faults in solar photovoltaic systems trigger immense reduction in power generation. These faults can occur when the photon energy from an energy source is obstructed by spatial entities like mist, dust, leaves, cloud cover, etc. Detection and isolation of the fault location is the only way to save the system from suboptimal operation. There are many fault detection techniques in the industry. There are techniques involving simulators, isolators, and reconfiguration techniques. Most of these methods require complex computational power, consume a significant amount of power to operate, and incur high manufacturing and maintenance costs. A circuitry which only turns on when there is a fault on a panel level and consumes extremely low power has been developed, and its operation will be demonstrated in this video. The proposed scheme involves the principle of the detection circuitry being powered by the forward voltage developed across the bypass diode or BPD. When there is a fault, the bypass diode is forward biased and there is a voltage developed across the terminals of the bypass diode. This voltage is amplified by a boost converter, and the output terminals of the boost converter are connected to an optocoupler. To verify and visually confirm the presence of a fault, an LED has been connected at the output terminals of the optocoupler. A glowing LED signifies the presence of a fault in the panel connected to that particular detection circuitry. For the initial tests of the proposed model, a DC-DC converter has been set up at the input to imitate a solar photovoltaic panel. A second converter has been set up with a fixed voltage of 3.3 volt and 20 milliamp to power the optocoupler. To simulate a faulty panel, a 1 volt 20 milliamp input is connected to the input of the circuitry in reverse polarity to emulate a forward biased bypass diode. The theory states that the detection circuitry is driven by this forward voltage of 1 volt. The turned on LED confirms the detection of a fault on the panel level. The next step is to simulate a healthy panel. For this, a 20 volt input is connected to the detection circuitry, which emulates a healthy panel condition. The theory states that the detection circuitry is turned off when the panel is healthy. The turned off LED confirms the inactivity of the detection circuitry and hence draws no power when in this state. For further demonstration, the input voltage was varied in a 15 to 30 volt range. All test conditions were successfully dealt with by the detection circuitry and the output was as expected. The 15 volt setup, the 20 volt setup, and the 30 volt setup.